In this part two of our discussion of the tides, I want to look at a few other features of the Earth, Moon, Sun system, and then also give you a kind of a quantitative feel for the differences in the tide quantities, the forces associated with the Moon and the Sun on Earth. So, primarily, tides are a gravitational effect, but the force itself is not what's primary. Rather, it's the differential force. It pulls harder on one side than the other. And we know that gravity is 180 times greater in magnitude than the Moon. But nevertheless, the differential tug of the Moon is greater than that of the Sun, about 2.5 times greater. So, now, if we look at this diagram, we see that the Moon tugs hardest on the front side, less hard on the back side. The average is about in the middle. So that produces a bulging effect on the front side, which is easy to visualize, I think. The backside bulge is maybe a little less easy. Let me give you three ideas, three ways to think about why you have bulge on both sides, as is clearly shown here. So the first one will be inertia. So think about pulling harder on this side. If you pull harder on this side is not forced to move as quickly. So because of its inertia, the water stays in place while the rest of the Earth is pulled away from it. It stays there and bulges. The bulge effect is because it wants to stay in place more than the front side, which is being forced to move. Okay, very closely associated with that, really the same thing, but I'm calling it a second way to think about it, is you're causing this to accelerate on the front side, the near side, more rapidly than the back side. So if it accelerates faster here, then this material is left behind. The gravitational acceleration, the G field, which is like the acceleration, is less. So the material here doesn't go as far in a given amount of time, so it lags and bulges, apparently bulges toward the left. And the third way to think about it is, look at each of these vectors. Okay, the biggest vector here, the average is about right there. That's the average size vector, the average force over this entire region. The smallest one being here. Let's subtract the average from everything else. When you subtract this off from this, you get a little vector forward, okay? A little vector forward. And that is the net, you could say, gravitational tug on the front material. If you subtract this off from the back, you'll notice a vector going the opposite way toward the back, which is a force dragging the water off to the left. So there's three similar but different ways of thinking about this phenomena. Hopefully that connected. Now, we have what's called Neap Tides, which are simply tides that are lessened due to the proximity, the relative proximity of the Moon and the Sun. So here's the Moon, and this black line is kind of corresponding to the stretching effect from the Moon. But the Sun is over here perpendicular. It's trying to stretch it horizontally in our perspective here. This is actually a top view. But these are opposing effects. So Neap tides are relatively smaller tides. And it happens at the third and first quarter phases of the Moon. All right, well now, there's also what's called spring tides. Not necessarily happening in the spring. The different tides can happen at any season. But it's where the tides spring up. Namely where the Moon and its stretching effect is being combined with the Sun and its stretching effect. And together they produce the largest tides, the biggest bulges on both sides. So that's Neap tides and spring tides. Then a couple other interesting things. This is a view from the top. So here we have the Earth spinning around. And here's a line connecting the Earth and the Moon. And if there was no, all other things being equal, if you see this outline here, this region, is the bulge pattern that would result just from the Earth, the Moon stretching the Earth. So the tidal bulges would be oriented along this line as shown, this gray area here. The blue area shows the effect of Earth actually spinning underneath this thing. So the moon is basically sitting out there. Yes, it's orbiting, but not real rapidly. So on a given day, as the Earth rotates, it's dragging, by friction, it's dragging that bulge forward, and that's this blue region. The blue region is the bulge that's been dragged. And so it actually is ahead of the whole thing. Now what happens is the moon now sees this extra mass here. The moon is not tugging at the center of the Earth, but it's actually at a slight angle because this additional mass, it's tugging above this center line. So the moon tugging like this, there's a vector component of force that opposes the rotation because the Earth is going to spin underneath this water, but the moon is tugging on this water bulge, keeping the bulge from continuing to rotate with the Earth, okay? And so the moon tugging back on that actually slows the Earth down as the Earth rotates under by friction. It's actually friction of the water against the surface of the Earth this way that causes the Earth to slow down. But the moon is responsible for the formation of the bulge and then keeping the bulge from just rotating with the Earth. So that's pretty cool, huh? As a result of that, that extra mass, the Earth is actually slowing by about 4 microseconds a year. So your days are actually getting longer. Isn't that great? 4 microseconds isn't very much, but if you extend that out over millions of years, it becomes appreciable, especially in billions of years. Now the bulge tugs the moon forward as well. So here we have this bulge. The Earth is pulling on the moon in this direction because of this extra mass here. The center of gravity is above this center line again. So in pulling this way, if you think of this as a vector, what I'm trying to do here with this cursor, there's that force acting on the moon in an angle has an upward component or a forward component. Really, I should say a tangential component. That tangential component increases the linear speed of the moon. So the moon's speed increases, and if that happens, it finds a new orbit out further away. So the moon is actually spiraling away from the Earth, and it's moving outward at about 2 centimeters a year. So the moon's orbital radius is increasing a couple centimeters a year. Now, the Earth also stretches the moon. We're not showing that in this diagram, but the Earth's gravitational differential tug pulls harder on this side than this side, stretching out the moon, and then that is actually going to cause the moon to tidally lock to the Earth, where one side of the moon faces the Earth all the time. I'll go into detail about that phenomena in the next video, after we finish a couple comments with our tides as experienced by the Earth itself. So to finish that thought, I want to give you a feeling for the actual quantitative relative sizes of these forces. So we have the sun pulling on the Earth. Now the Earth is to scale in size with the moon, not with the sun. The sun would be a lot bigger than this, but that's okay. It's not the important point here. On the far side, that vector is a little smaller, and again, 17/1000ths of 1%, so not very much. The moon, we have near side and far side pulls that are 7% difference. So now what I'm drawing for you is a vector that represents the size of the force of the sun on the Earth, this whole thing here. And right next to it, I'm going to draw for you the force on the far side of the Earth by the sun. You can see how small of a difference there is between the sizes of those vectors. So here's the sun on the near side, and here's the sun on the far side, pulling just about as hard. Except I've really just lied to you pretty profoundly. Because in actuality, If I would have told you the truth here, you wouldn't see any difference at all in these sizes. If I really gave you a 0.017 or 17 thousandths of 1%, hello? No, it would be a lot smaller gap than that. In fact, that difference I showed there is 100 times too much. It's only 1/100th of that relative difference, but that'd be far less than a pixel. You would see the exact same vectors shown there. So hopefully that gives you a picture to ponder. Then there's the moon. So there's the moon force. Isn't that beautiful? But it really isn't, because remember I said the moon force is only 1/180th of the sun. Well, does this look like? Does it look like this? 180 of these would be what this is? Well, not at all. In fact, that is 10 times too big. So it'd have to be a tenth of that, which is really, after I show a corresponding feature here, this is 2.3 times bigger gap than this. But, you know, I'm not really, but again, this gap is 100 times too big, like this gap is 100 times too big, all right? So here's the actual size of the moon force compared to the sun force. If the sun force is really this vector, then the moon force is just that little blip there. I can't even put an arrow on it. And the far side of the moon would be 7% difference than that. And that would be noticeable, but still very, very, very tiny. So that's my attempt to give you a feel for the actual quantities here. And now you have more knowledge about the tides than perhaps you wanted, but hopefully that's not true either. And in the next video, we'll visit why the Earth and the moon are tidally locked, where the moon only shows one face of itself to the Earth.